Hello everyone, today I'll be introducing you to a new rule in calculus, and its name is the quotient rule. So when people first encounter this, I think the most common reaction is thinking that it's really difficult because it has quite a long expression over here, so f prime of x times g of x minus fx times g prime of x, or if I divide it by gx squared, which seems really hairy and really difficult to remember, but really all you need to remember is that it's basically the same thing as the product rule, but instead of a plus you have a minus, and all that is divided by the denominator function squared, so g of x. So if y is equal to f of x divided by g of x, then assuming that g of x is not equal to 0, because then of course you can't divide by 0, then this is the result you need to be using. So yeah, I'm just going to show you one quick motivation to actually know this rule. And the reason is, I haven't made any videos on finding trigonometric derivatives using limits, but it's one of those things that gets really difficult because it's quite long. And tan of x is basically the same thing as sine of x over cosine of x. So there's no reason why we shouldn't use the quotient rule here in order to find the derivative of tan of x. So let's just crack on with that. So we can define f of x as sine of x, right? Because if this is sine of x and this is cosine of x, y is equal to tan of x, just like I have here in this trig identity. And now this is another trig identity which I'll be using later on in this video, so don't worry about it for now. Okay, so f of x is sine of x, and g of x we can define as cosine of x. And of course, we still consider that boundary, that cosine of x shouldn't be 0. Okay, so how do we start from now? What you can do here is, and I'm going to be using the derivative, the Leibniz derivative notation here, because that's often the most intuitive for using. It's not the easiest to write, but it's the most famous kind of notation for derivative. So f prime here is the derivative of sine of x, and then that is times by g of x, so cosine of x, and all of that is subtracted by sine of x, which is essentially our f of x here, times the derivative of cosine of x. And you don't have to know what those derivatives are, but for now I'm going to tell you, because I'm going to make a video about trigonometric substitution and trigonometric derivatives in calculus, but for now let's just tell you what those derivatives are. So the derivative of sine of x is equal to, surprise surprise, cosine of x, and the derivative of cosine of x is equal to minus sine of x. And actually it's really interesting because if you keep differentiating those, you just get the kind of, because you see here that you end up having cosine of x, and then the next derivative applies to that cosine of x. So it's like almost like a cycle, because then if you differentiate minus sine of x, you get minus cosine of x, and if you differentiate that, you get sine of x. So it's a loop. But I'm not going to get into that. I'm just going to show you what we end up having here. Okay, that's our gfx squared. Okay, so we end up having this derivative over here is cosine of x. So cosine of x times cosine of x is equal to cosine of x squared. Or the two can be here as well. Like, it depends on. I just wanted to facilitate what this expression means, so I'm just going to show you that it is. If you have cosine of x with the square symbol here, it's the same thing as if it's here. And then that is minus minus by sine of x times derivative of cosine of x, and we said that is equal to minus sine of x over here. So what is minus sine of x times minus sine of x? That is the same thing as sine of x times sine of x, because the subtraction here is doubled, so it cancels out. And then this becomes a plus symbol. So, and here actually I showed you that this is equal to 1. So you have this expression over here. And as we said before, this is equal to 1. So it's the same thing as 1 over cosine of x squared. Actually, 1 over cosine of x, I don't know if you have done further trigonometry in A-level maths or whatever course you're taking, but that is the same thing as the secant function squared. So that's a very kind of famous result in trigonometrical calculus. It's like the third most elementary trigonometric result you get here, because tan of x is used all around in calculus. So yeah, just in case you don't know, I don't know if I'll introduce this in new videos, but I think it's quite useful to know that 1 over cosine of x is secant of x, 1 over sine of x is equal to the cosecant of x, and that 1 over tan of x is equal to the cotangent of x. Those are just like, they're basically names, but there's nothing new about those trig functions. They're just the inverse, as in like 1 divided by the 3 basic trig functions. So this is just a name, but you can think of it as just 1 over cosine of x squared. Okay, so we have solved this, and this is interesting because you have to use 2 trig identities. But now let's focus on the new example here, which doesn't have any trig function here. So in a previous video we said that for any e to the power of kx, its derivative will be k times what we started with, so k times e to the kx. But what if k is equal to 1? Then what happens is the derivative of e to the power of 1x, which means the derivative of e to the power of x, is the same thing as itself. You end up getting e to the x again. So that, just remember that. There's also a proof using something called logarithmic differentiation. I don't know if you've heard about it, but I'm going to make a video about it next, so yeah, keep watching. So we just kind of use this limit over here, not the limit, sorry, the definition in terms of f of x times f of x and g of x. So this is our f of x and this is our g of x. But what happens here? If we try to solve it, we get f prime of x times g of x minus f of x times g prime of x, and that is, let's just quickly show what that actually means. And actually, before I get to actual differentiation, I just want to note that both in integration and differentiation, in both of them, you can do a little trick with constants. So this expression over here is the same thing as this expression over here. Now, this is much easier to derive, right? So a little trick you do is you just differentiate that and then times it by that constant. You can do it in integration and differentiation, and it's a really useful tip. So then we get 1 over 5, 1/5 over times, we said that f prime here is the same thing as e of x, because e of x differentiates and integrates to itself, basically. So that's times g of x, not g prime of x, but gx. So that's just the same thing as here, as what we have here, our new g of x. And then we minus e of x, because its differential and the function e of x are the same, times 2 of x, because I hope you remember now that according to the power rule, all you do is just move the exponents of x to its coefficient side and then minus it by 1, and then you end up getting 2 of x, 2x. And then all of that divided by x squared, and that is squared because you have g of x squared, remember? Then we just factorize that and we replace x squared with x, replace the 2x with 2, and then we remove this squared symbol here because we just don't need it because we have divided all sides by x here. So then we have e to the x times x minus e to the x times 2, that divided by that is divided by, because this is equal to x to the 4, right? It's not like you just ignore the fact that there's the brackets here. So when you divide both sides by x, that's what you get. And then we can't really factorize this anymore because there's no more kind of universal shared x symbol here. Like there's no x term here, so we just kind of leave it like that. But what we can do is we can return the constant here. Then we end up having this so it's kind of like returning the number you tried to get rid of before in order to facilitate the differentiation. What we have now is we can just quickly factorize this, and what we end up having is we'll end up having e to the x and x minus 2, and we are done.